So, we are going to continue on approximation algorithms, and today we will actually do some randomized approximation algorithms for maximization problem. Okay, we haven't seen too many maximization problem. We have seen vertex cover, TSP, scheduling, set cover, all are minimization problem. The couple of popular maximization problems are this max independent set and max click. Unfortunately, there are no good approximation algorithms for them at all, and there are some theorems that tell you that good algorithms, approximation algorithms are not possible as well. So, the problem we are going to look at is this max sat problem. So, its input is a CNF SAT formula. So, let us say it is a 3 CNF formula, which is a canonical NP hard problem. So, it is a Boolean formula with n variables, m clauses, each clause is an OR of variables. The satisfiability problem is, given such a formula, is it satisfiable? The max sat version, the optimization version is, given such a formula, what is the maximum number of clauses you can satisfy? So, the formula may or may not be satisfiable, but I want to know what is the maximum number of clauses that is satisfiable. Now, clearly, this is also an NP hard problem, because if I can solve this, I will be able to answer satisfiability question, right. If the maximum is the full all formula, all clauses, then you know it is satisfiable, otherwise it is not. So, this is a sort of a generalization. In fact, this is NP hard even for 2 CNF. Okay. Let me just make a remark, and there is a reduction from 3 CNF to max 2 CNF. Okay. It is clearly NP hard for 3 and above, because this is a more general version of 3 SAT, but it is NP, but 2 SAT, you know, testing whether it is satisfiable or not is polynomial time solvable. But if you get the answer it is not satisfiable, I want to know what is the maximum number, or can you satisfy at least so many clauses. That is NP hard. Okay, so, we want to design approximation algorithm for this, and it is a maximization problem. Okay. So, let us just look at some picture of approximation algorithms in general. For minimization problem, suppose this is opt, right, for some instance, and if it is a minimization problem, where would this algorithm solution lie? After opt or before opt? More than opt or less than opt? More than opt, right, because opt is the minimum. So, you can't get anything, we are always looking for a feasible solution in polynomial time. So, minimization problem will give you something here for minimization approx algorithm solution. And the way we wanted, the way we were bounding the quality of the approximation solution is that this is not too far from the opt, right. So, if opt is something, 2 opt may be something like here, then we argued for a number of problems that this solution produced is less than or equal to, it will always be greater than or equal to opt. We argued that it is less than or equal to 2 times opt, half 1.5 times opt, or log n times opt kind of arguments we had to analyze the quality of the solution. But if I want to talk about maximization problem, if this is opt, for maximization problems, the solution produced will be somewhere here, because it cannot produce bigger than the opt. right. So, now what we want to argue is that it is not too far. So, what sort of argument we want to give? So, solution produced is greater than, less than? Greater than. It is less than, it will be less than opt. We wanted to show that it is greater than or equal to some alpha times opt, and this alpha would be my approximation ratio. Okay. For minimization problems, we want to show the solution produces at most some alpha times opt. Here I want to show that it is at least some alpha times opt, and bringing this alpha as close to 1 is the goal here. Okay. So, back to the max sat problem. And your input is something like this. So on and so forth. There are some m such clauses, right. And our goal is to come up with an assignment to the variables that satisfies maximum number of clauses. Okay. Suppose I just do some random experiment. What does that mean? So, for every variable I toss a coin, if it comes head I will set it to 1, and if otherwise I set it to 0. Okay. So, that is a random assignment. So, often it is very important to distinguish between random and arbitrary. People will confuse, right. Let us take a random assignment. What you probably mean is, let us take an arbitrary assignment, arbitrary Hamiltonian cycle. When you say random, it is a loaded word. Here I am saying I perform this specific random experiment. This is a fair coin, it comes back head with probability half and tail with probability half, and I toss this coin, and if I get one head I set it to 1, and if I get tail I set it to 0, right. So, randomly, not just randomly, I also do it uniformly, which means that the equal probability, set each variable to 1 or 0 with probability half. Okay, so, this is a randomized algorithm. So, what is the output of my problem? Output is an assignment, right. Output is an assignment. So, I have given you an assignment. Toss coin, if it comes head I will give you 1, otherwise 0. Okay. And I do not need to satisfy all the clauses, I am asked to satisfy as many clauses as possible. So, clearly the assignment is sort of a random variable, because different coin tosses will result in, or different outcomes of the coin tosses will result in different assignments. Okay. So, let me just get into distract a little, digress a little bit and talk about randomized algorithms. Okay. I briefly did last week. So, in general, when our deterministic algorithms take some input and give some output, right, whether it's sorting, Hamiltonian cycle, coloring, BFS, whatever. Randomized algorithms also take some random input, right. So, in between, apart from my formula, I can, so the way actually implement it is you consult a random number generator, and it gives you something, and based on that you make some choices, right. So, the important thing to notice is the output does not just depend on the input, it also depends on the random input, the random choices the algorithm makes. So, for the same input you could have different output if you run it multiple times, right, because of it just does not depend only on the input, but also depends on the output. Okay. So, one example randomized algorithm you would have all hopefully seen is this quicksort, right. So, how does a randomized quicksort work? You what? Choose a pivot randomly, right, choose some element. some index in your 1 to n randomly, and then, so first compare all elements with this pivot. Elements that are less than the pivot go to the left, elements that are greater than the pivot go to the right, but among them you need to sort them, which you recurse. Okay, that is quick sort. Okay. So, now the behavior of quick sort, I told you, does not depend just on the input, but also depends on your random pivot. Okay. Now, when I tell you behavior, there are two ways the behavior can change. The answer may be wrong, I mean the answer may be different at different times. That is one kind of change in difference in the behavior. The other difference in the behavior is that what is the other difference in the behavior? What can change? What can vary? The time can vary, right. So, these are the different types of randomized algorithms, Monte Carlo and Las Vegas, right. 2-mark question, right. So, what is Monte Carlo? Here the answer can vary. For example, if you are looking at a decision problem like is the number prime and you are running a randomized, these algorithms are actually called probabilistic algorithm. It comes back and sometimes it may say yes, sometimes it may say no. So, it may be making an error also. The algorithm answer can even be wrong in the case of decision questions, but we will see that in the case of my MaxSat kind of a problem, the answer will be different, right. Sometimes it gives you one assignment, sometimes it gives you another assignment. So, that is how that answer could be different. And Las Vegas is the answer is always right, the time varies. So, in the case of quick sort, is it a Las Vegas or a Monte Carlo algorithm? Las Vegas, because at the end of it, it actually sorts, no doubt about it. You take a pivot, partition, recursively sort each part, at the end of it, it will finally give you a sorted list. So, that output will be the same, whatever you run at a different time, but what changes is the running time. The running time depends on the random choices, the pivot it makes, right. So, then because in randomized algorithms, you do not look at worst case. Okay, you could argue worst case based on the worst random choices kind of thing, but a typical way you analyze a randomized algorithm, you look at its expected behavior or its average behavior. Okay. Average over what? All possible. There are two different ways of analyzing a randomized algorithm. So, suppose for a fixed input, right, let us look at quick sort. If it picks some certain kind of a pivot, it takes certain time, and if it it is not just one pivot, there is a sequence of pivots, because every recursive step you are picking pivots. If it picks a certain sequence of pivots, it has a certain time. If it manages to pick certain kind of pivots, it has a certain time, and so on and so forth. So, average over what for the fixed input? Average over the choices, the outcomes of the random numbers you picked. So, now you look at all possible random choices the algorithm makes for the fixed input, and then you look at the average over average number of comparisons, and that is the expected behavior. Okay. So, there are two kinds of randomized algorithms, there are kind of algorithms where randomization is built into the algorithm. There is a deterministic version of quick sort, where there are no random choices. What is the deterministic version of quick sort? You just pick the first element as pivot, partition it and recurse. There are no randomness. Now, this algorithm will behave differently for a different kind of input. For the same input, it will have the same behavior, because there is no random choices here. But for certain kinds of input, it will run fast, certain kinds of input, it will run slow. So, then you look at average over all possible inputs. Okay, when you talk about average behavior of a deterministic algorithm. Here, average behavior of a randomized algorithm means you do an average over all possible choices of the input. So, both versions of quick sort are there, and both kind of average analysis will result in, and there is also a theorem that you can actually way to translate results there to here. Okay, it's just a big theorem there. So, what we know is a quick sort is order n log n on average. Now, how do you analyze the expected behavior of quick sort? let's look at I want to just give a feel for it, and then we'll get back to our MaxSat problem. Okay. How do you analyze the running time, number of comparisons of a randomized quicksort where you randomly pick your pivot element? So, let us write a recurrence relation T of n, right, quicksort expected runtime. You pick a pivot and then you are comparing. So, I am counting only comparisons. Then you are comparing one element with everybody else. So, how many comparisons? N minus 1. Okay. So, you make n minus 1 comparisons plus what? Now, you are recursively solving the problem on the left side and the right side, right. So, it will be T of whatever the size of the left side is plus whatever the size of the right side is, right, after your partitioning. But the important thing is this left side and right side are random variables. The worst case, it could be n minus 1. One of them could be n minus 1, the other could be 0, and then if you do an analysis of this recurrence, what will you get? N square. So, that is the worst case behavior. Now, if I want to talk about average expected behavior, then these numbers I have to run through all possible choices and do the average, right. So, for example, what is the probability that L is 5, right. So, I picked a random pivot and did my partitioning. Some of 5 elements landed on the things less than that. What does that mean? What is the pivot? Pivot is the 6th smallest element. You manage to pick in your random choice 6th smallest element. What is the probability of that? 1 by n, because if you are truly random, the probability that you will pick ith smallest element for any I is 1 over n, because you are not biasing, you are just. So, the probability that this number is any such number is 1 over n. So, my average behavior would be n minus 1 plus 1 by n is the probability by which this will be some I minus 1 and this will be n minus I minus 1 size of R, because R is just the remaining things over all possible values of I going from 1 to T of 0 is 0. This is all the recurrence relation. Now, solving this is not immediate, you can't just apply your master theorem or any such thing and get it, but there are ways to solve this, and if you do the calculations, you will see that it pops out as n log n. When somebody is interested, I can tell you during the breaks how to solve such a recurrence relation, but the key thing is to get this. How do I compute the expected runtime? Okay. That if I am doing a random pivot choice every time, then first I do n minus 1 comparison, sorry, it is not n plus 1, it is n minus 1. And after that, 2 recursive calls, but I have all possible choices for the recursive calls. There are n choices, and so I average over all this, and that is the number of comparisons. Okay, so this is how you analyze randomized quicksort. Now, let us come back to our MaxSat problem, and what did I do? I just randomly set my variables 0 or 1. The running time of the algorithm is trivial, it is linear time, okay, I am not doing anything. Now, what is it we want to analyze now? Number of clauses satisfied, right. This is the goal in approximation algorithm, which is the quality of the solution. How good is it compared to the optimum, right. What is the probability that the first clause is satisfied? What is the probability that it is not satisfied? All these variables should be set in a 0, right. X 1 must be 0, x 2 must be 1, x 5 must be 0. If that happens, this will not be satisfied. In any other case, it will be satisfied. If you look at these 3 variables, the only time it will not be satisfied is if x 1 is 0, x 2 is 1 and x 5 is 0. And I am setting these variables 0 or 1 with probability half independent of anything else. So, probability that all these events happen together is the product of these probabilities. Right? Probability of events happening together, probability that x 1 equal to 0 and probability that x 2 equal to 1 and probability x 5 equal to 0 is 1 by 2 into 1 by 2 into 1 by 2. So, it is 1 by 8, and in any other case, another way to think about it, how many possible assignments are there for these 3 variables? How many? 8 possible assignments, and how many assignments will satisfy it? 7 out of the 8 will satisfy it, exactly 1 will falsify it. So, probability that this clause is satisfied is 7 by 8. Now, you can argue this for each clause independently. So, probability that C I, any clause, is satisfied is 7 by 8. So, now we can only talk about the expected number of clauses satisfied, because this is a randomized algorithm. So, expected number of clauses satisfied is, there is a very nice again theorem in probability theory, is linearity of expectation. Expectation of a sum of random variables is equal to sum of the expectation of the individual random variables, right. So, this is expected is summation I equal to 1 to m expectation of clause C I equal to 1. Now, clause is satisfied or not. So, this clause variable either takes 1 or 0, and it takes 1 with probability 7 by 8 and 0 with probability 1 by 8. So, this number is basically 7 by 8. So, this is equal to 7 by 8 times m. So, the expected number of clauses satisfied is 7/8 of the total number of clauses, which is equal to, or which is greater than or equal to 7/8 times opt, right. What is the optimum maximum number of clauses you can satisfy? M. M is the total number of clauses. So, maximum you can satisfy is m. So, opt is less than or equal to m. So, this is a randomized approximation algorithm whose quality of the expected solution produced is at least 7/8 times opt. Now, there is a very nice way to de-randomize this algorithm and make it actually deterministic approximation algorithm. I will just tell you that, because it is also very nice to know. So, again when I say expected, expectation is over something. What is it over here? Average over the random choices made by the algorithm. What is the random choice? It is a random assignment. So, expectation over all possible assignments is what it is. Okay. So, one way to think about it, because of we did a uniform probability, is that you take your formula and set some assignment to the variables and count the number of clauses satisfied. Do some other assignment, count the number of clauses satisfied, and take this entire average, and it is telling you is at least is exactly 7/8 times m, right. Because what are the random choices? These are actually the assignments, just random assignments. So, I am picking, what is the probability that my random assignment will make the x 1 to 0, x 2 equal to 0, x 3 equal to 0 and x n equal to 0. What is the probability that I will set every variable to 0? 1 by 2 power n, because there are n variables, same argument, right. So, each one is set to 0 with probability half, and all of them should simultaneously happen with 1 by 2 power n probability. I am going to set that, right. So, the way to think about it is 1 by 2 power n times the number of clauses satisfied by setting all 0 0 0, all this, all that, all of that is actually 7 by 8, which is same as saying take your formula, run it over all assignments, take the entire average, and that is 7/8 times m. Okay. Now, here is a very cute, it is a very useful trick to de-randomize the algorithm, because you just have to think about this average slightly differently. So, what we are doing is think of a binary tree, right. So, I am setting x 1 equal to 0 here and x 1 equal to 1 here, and then I am setting x 2 equal to 0, x 2 equal to 1, dot dot dot. At the end of it, you have one full assignment, and this statement is simply saying that if you put this assignment, go to your formula and see how many clauses you satisfy. Put this assignment, go to your formula, count how many clauses satisfied, do this and take the average over 2 power n. This statement in a very clean simple way proves that this number is actually 7 m over 8. Okay. So, now which means there is at least one assignment here which satisfies at least 7 m over 8 clauses, right. We saw it some lecture before, that if the average of something is 83, at least somebody must have gotten greater than or equal to 83. If everybody got less than 83, the average cannot be 83 or above. So, at least one of these assignments satisfies at least 7 m over 8 clauses. Now, I want to deterministically find that assignment. Then I will have a deterministic approximation algorithm in polynomial time, right, because what is our goal? We want an assignment that satisfies at least 7 over 8 times opt, right, and I don't want to get, I want to get rid of this randomization and come up with a deterministic algorithm which finds it. One way I am doing it is I will randomize it and de-randomize this algorithm. Okay. So, I want to deterministically find, so let us say this is my good assignment. So, this green is some good assignment satisfies greater than or equal to 7 m over 8 clauses, right, because this is the optimum, this is my objective. I want to satisfy at least as many clauses as possible. So, this is my objective value, I want to maximize it, and somehow deterministically I do not know this, my averaging argument tells me that there is at least one and I want to find that. Okay. So, this is called method of conditional expectations to de-randomize some of the randomized algorithm. So, one way to view this average is that half into this average plus half into this average is at least 7 m over 8, right. Look at the leaves of this assignment, this subtree, look at each leaf corresponds to an assignment, count the number of clauses and add them and do the same for here and do an averaging, right. So, this plus this by 2 is at least 7 8 over m, because I said the total average is 7 m over 8. So, this average plus this average by 2 is 7 m over 8, which means that one of the averages must be at least 7 m over 8. Okay, this is a simple averaging argument. This average plus this average by 2 is at least 7 m over 8. So, at least one of the averages must be 7 m over 8, which means let us say this leaf is sitting in this. Okay. Now, what I do is I compute it turns out I can compute these two averages very easily. How? We did that, we just computed the entire average very easily, right. How did we do this? This is how we did. So, what you do is set x 1 equal to 0 in your formula, x 1 vanishes, remaining variables set them with probability half and compute the expectation, exactly the way we did here. Similarly, set x 1 equal to 1, x 1 vanishes again, compute the average on the remaining variables and see whichever average is bigger, take that path, set your x 1 to 1 or 0 appropriately, and that takes you to one path, one direction, and if you keep repeating this, you will eventually get one path in linear time. And that we know that finally what we know is that, so all we are saying is that average here is greater than or equal to the overall average. That is how I chose this, because this has a bigger average than this. And then once I get here, I will go to its one of its two children, whichever average gives me the bigger average, and I come all that, and I know that the expectation here is bigger than or equal to the expectation here, but there is no expectation here because all variables are set. So, the way to think about it is that I have done some partial assignment, I fix some partial assignment and do an average over the remaining. And when I come here, I fix the entire assignment. So, I will be able to come and deterministically get to that assignment that satisfies at least 7 m or 8. Okay. Okay. So, it's a technical concept, but not very hard if you just look at it and stare at it for a couple of times. So, what is the end of the story? We can deterministically find an assignment to my given 3-SAT formula, which satisfies at least 7/8 of the total number of clauses. In this world, the solution produced is at least 7/8 of the opt. It will be less than the opt because it is a maximization problem, I am approximating it, but it will be at least 7/8 of the opt and it is a 7/8 approximation ratio. Now, question, what if I apply this for max 2-SAT? I said max 2-SAT is also NP hard, even though satisfiability question polytime solvable. If you want to know the optimization problem, it is NP hard. Now, I do the same thing. So, now every clause has exactly 2 variables and I randomly set every variable 0 or 1 and I get an assignment. What is the expected number of clauses satisfied? 3/4 times m. Why? Because if you pick any clause, it has 2 variables, the probability that it will be falsified 1/4, because this is half, that is half. So, if I apply this, expected number of clauses satisfied is at least 3m/4. And for general max SAT, even if there is only one variable in each clause, that also is NP hard. If I apply it, I will get m/2. I can, so this will give you. So, the larger the number of clauses, closer to 1 you will get in the approximation ratio. Remember, sorry, larger is the length of the clause, closer to 1 will be the approximation ratio, right. It starts from half, 3/4, 7/8 and so on and so forth. So, you can, for a 4-SAT it will be so here is a maximization problem. You want to maximize the number of classes satisfied and you have good approximation algorithm through the randomization de-randomization route, and the whole thing can be de-randomized exactly the same way using method of conditional expectations. Okay. And in fact, let me also put a note here, we won't talk about it. The approximation ratio can be improved using linear programming. At least for max SAT and max 2-SAT. There are linear programming, there is semi-definite programming, there are some, these are very recent, like last 10 years research, where the people have improved approximation ratio using some more sophisticated formulation. The key thing is, what is the upper bound for the optimum we used? Remember, in the minimization problems, we used a lower bound for the optimum, right. For vertex cover, it was matching, for TSP, it was the spanning tree and so on and so forth. For maximization problem, we use an upper bound for the optimum. What is the upper bound we used here? Number of clauses. Now, that may not be a good upper bound. So, you actually, so you want to use a better upper bound. So, linear programming actually gives you better upper bound, and using that you can actually improve the approximation ratio. Okay. And these are all, if you are really interested, they are all accessible to you. Somebody who is really who has been following can take that extra step, read, and you will be able to follow the better improved approximation algorithm. And these are in, they have made it to the textbooks now.